exciting day. I was like, almost last little bit. I was like, basically two days of lecture left. And that is the semester. Whew, thank goodness. Huh? I was like, oh, you guys are coming back next year though, right? So I was like, not that big of a deal. Like, when you're like graduating, then it's a big deal. But like, you're just coming back. It's like, okay, little reprieve, and then back to it, right? Yeah. All right. So we were looking at this example problem. All right. We identified, we have 3 points, want to find the triangle, all right, area of the triangle that combines them. So we made vectors, and the biggest thing about vectors is picking the same starting point. And we identified the area of a triangle is actually, all right, the magnitude of the cross product, and that's what we did last time. So in order to get the area, all I have to do is the magnitude of the cross product, and then multiply it by 1/2. So square root 8 squared plus 4 squared plus 4 squared. Which yields 4.9 units. And then for context, squared, since that's an area. So the cross product is very, very helpful when identifying something like an area. So the triangle, right, that's 1/2 of the magnitude of the cross product. But if you were just doing the area of a parallelogram, so this is area of triangle, which is what the question was actually looking for. But as a note, if we were looking for the area of the parallelogram, that is just the magnitude of the cross product. So identifying the cross product is very, very helpful. One of the biggest things that we're always talking about with a cross product, though, all right, is finding a vector that is perpendicular to a plane, all right? By definition, all right, when you have 2 vectors, no matter where they are in space, they create a plane, okay? A set of values, all right, along a particular axis, all right? So again, given these vectors, I mean, we're out here in space, but the cross product, the whole point is when you cross 2 vectors, right, using the right-hand rule, you find a perpendicular vector to that plane. And a lot of times what else we care about is not just a perpendicular vector, but that is the definition of the cross product. But how about a unit vector? What does a unit vector mean? We haven't done any of the home fun yet. We're like, that's like next week's problem. Unit vector means a vector of length 1. All right, a vector of length 1. So by definition, all right, the cross product, this is perpendicular to the plane PQR. That is, by definition, as soon as you do a cross product of 2 vectors, you found yourself a perpendicular vector. In order to make that a unit vector, all we have to do, and for physics completion, for physics consistency, let's call this the normal vector, since that is the perpendicular vector, which is just going to be our vector, which is u cross v, divided by the magnitude of the cross product. Both things that we already calculated. So I have my vector 844. Divided by 9.8. And that is a unit vector that is perpendicular to the plane PQR. As a note, all right, that is the specific one that we found given u cross v. Could I also have done v cross u? Answer is yes. All right. The only difference is that it changes direction. Instead of coming this way, it would have gone this way. So I can actually even say that whole thing is plus or minus, positive or negative that. Both of those are unit vectors perpendicular to the plane PQR. And so we've created two different unit vectors. Now, all I actually needed was the initial one that we found, because that is a specific one given that information. But it works out just as well because I picked u cross v, but you could have picked v cross u. All right. It'll always come out. It's the same, just opposite signs. All right. Okay, so cross product is a big thing. So application is our favorite part, right? We are in application now, right? And the best part about application is lots and lots of word problems. So the biggest application of vectors always comes down, all right, to force, all right? Physics is one of the biggest applications of vectors. And so we're going to look and we're going to practice these force equations, because creating these force equations is what helps us apply vectors most realistically. So there are three forces acting on an object as shown in the diagram below. All force measurements are in newtons. The angle measurements are as follows: alpha, beta, gamma. All right. Then I want to find the x and y components of each of the three poles, and then use the components to find the magnitude and direction of the resultant of the three poles. So what that means right there is this is not an object that is stationary, all right? It was stationary, then we decided to pull in three different directions. So three people are pulling on this object, right? And we need to identify what happens from that. Notice that how alpha, beta, and gamma given are different. This is not bearing. All right, since this is not bearing, we have the proper x and the proper y, which means if I'm given alpha here, this guy is 32 degrees, what angle do I actually need? So that's what I have. I have the angle off of the y-axis, all right? From y to 32 degrees, I'm given the bearing of that force. In order to actually calculate the components, what do I truly need? X. I need it from the x. All right, gamma is given similarly, okay? Beta is the only one that's actually given properly, all right? Off of the x-axis in order to calculate the resultant of poles. Also, this isn't 3 dimensions. If I was in 3 dimensions, actually, I do want bearing angles because I still want off of the positive x, positive y, positive z. Okay, so, all right, from this, that means I have to do 90 off of that, and so what is that, 58? So I actually need that guy. Oh, no, I do have the right one here for gamma. So that is off of that, which is 53 degrees. And this guy I have is 31 degrees. Okay, so with that information, then we can create our physics equations. Okay, I've left two big things blank here. So I have my 58 degrees. Was that what we called F1? Okay, yeah, 788. So with that, I need to identify the angles that the signs of the functions that correspond to that. So, all right, in this direction, all right, so we're calling this guy force 1, all right, and I mean, the easiest way is F1, F2, F3, and it doesn't really matter however you label them. I'm just starting there. So with that one, and I just wanted to start with this one because, all right, going this direction, all right, is cosine positive or negative? Negative. Is sine positive or negative? Positive. All right, so for each of those, we have to adjust negative x, positive y. All right, and that one was 788. The magnitude of my force is exactly the amount of newtons that is being implemented. And then it just worked. And then that turns into values. And multiply the 788 through. And then as a note, so this is our general equation, right? This is something that breaks an equation into a magnitude, and a direction. And remember that this becomes a unit vector because it's just sine and cosine. And I didn't want to write the form alpha because it was really 90 minus, this one's beta. Okay, this one will be beta. So with this, all right, it's whatever your angle is, which creates a unit vector, and the force, by definition, if we just use the newtons, all right, force as a number when it's presented as, right, so pounds is actually a force measurement, right? When you say 150 pounds, it doesn't actually have a direction associated with it. That is the magnitude of the force being applied. All right, so force 2, all right, 31 degrees, 985. Then I need to double check. Yes.
31, not 32.
Oh, geez, did I write it down? Oh. Okay, so 31 degrees. Then, as always, we need to check the direction. Given how we set up our scale here, is cosine positive here? Sine positive here? Oh, so that's a nice easy one. And then calculate away. And then lastly, we have gamma. Okay, 53, 411. 411 for our magnitude. And all of this is just using that concept of reference angles, right? This is all stuff that we've actually done before. That's why I only need 53 degrees instead of saying that that's 180 plus 53, whatever number that would be. All right, and then down here, given our orientation, is cosine positive? Is sine positive? Oh, okay. So they're both negative. And again, that's what orients the forces. I mean, the angles don't do that, right? It's the sign that's associated. And calculate away one last time. Okay, so part A actually said find the x and y components of each of the three poles. All right, so that actually is exactly what we did here. Okay, then use the components to find the magnitude and the direction of the resultant of the three poles. That is, find the angle of the resultant force, the resultant vector, and the length. Okay, so first things first. I want to find B now. I want to find the resultant vector. Guess how we do that? If I have three forces in three different directions, and I want to find, well, what actuals, so right, I have negative in x, negative in y, positive in x, positive in y, negative in x, positive in y. I have almost every combination that we could. How do I find how far, which direction, and how far is it actually going in x? All right, so I have negative 417, positive 844, negative 247. Guess what we do with those? Add them. In order to find the resultant force, all I have to do is F1 plus F2 plus F3. I add the three vectors individually in order to find the resultant. And since everything is component-wise, right, given how we have it written here, which is the benefit of turning it into, you know, a vector form, I add all the x's together, I add all the y's together. So even though it may be complicated-ish, all right, to break it down instead of just saying, well, I'm pulling, you know, 788 newtons at 58 degrees that way, all right, putting it in terms of x and y, I can actually find the resultant of three poles. So actually all we have to do is add all the x components
And then just, I guess, just so we can, 844. 417 minus 247 in the I direction plus, and then this is just approximate. I'm using the actual numbers. In the J direction yields 179.39I plus 847.34J. So that actually gives me my resultant vector, in which then, just like we did on our other ones, I want a graph. And I can rough sketch this just given orientation. What quadrant is this resultant vector in? Yeah, the first quadrant. Okay, so let's see, 170 out, 180 out on X and 850 up on Y. It looks like that. All right, there is our resultant vector. And I know this value down here is 179.39. This value right here is 847.34. From here, I can calculate the angle. Guess how we do it? What shape do we love? Triangles. That makes a right angle here. What? And I'm looking specifically for that. What trigonometric function relates, right? I have that distance. I have that distance. Tangent. So we can do theta equals tan inverse. So I'll just jump to the right. Tan inverse of opposite 847.34 all over 179.39 in order to actually get, right, the angle off. And that becomes 78.05 degrees off of the positive x-axis, because we knew our orientation. And furthermore, right, in order to find the length of the vector, okay, so it asked, right, that is find the angle of the resultant vector and the length. I mean, we found the resultant vector, but we also want to find length. That's a common ask. How do I find the length of that vector? That is, how long is that guy? Pythagorean theorem, which is also, right, the special case of doing what calculation? The length, AKA the magnitude, right? We talked about this. The equation, all right, magnitude of the resultant vector. This is just the Pythagorean theorem is just a special case of the magnitude. And it's all the same, right? And whether you use Pythagorean or magnitude, it is exactly the same, all right? Square root of 179.39 squared plus 847.34 squared. Square root. Gets us 866.12. We are in context, so what else do I need here? Thought I heard it? Newtons. All right. So, all right, the length, AKA the actual magnitude of the force presented resultant from these three vectors being pulled in different directions, all right, is 78 degrees off of the positive x-axis with a force of 866 newtons. And that's pretty cool. I was like, we actually are able to calculate that. These concepts extend to 3 dimensions because when we move in 3 dimensions, right? But I was like, that is the general concept. All right.
We love these force equations. All right, so this one, okay, there is a weight, 2,200 newtons supported by a ring that is supported by two cables hanging in the corner of a room. One cable is at 60 degrees. The other cable is parallel to the ceiling. Refer to the figure below here. Find the force on the ring, write in vector notation. So at this point, this is in static equilibrium. Okay, so this is not three things resulting in a pole, all right? By definition, the ring is static, all right? It's not moving. We have all these angles, but nothing is being changed. Also, the force is coming off of the ring, all right? So we got F1 over here, F2 over here, and F3 down here. So same thing, we have three forces coming off of this ring. As a note, this 60 degrees doesn't help me, okay? Because the force, right, it's this direction. It's always away from whatever that static equilibrium is. It just happens that all those forces are going to be equal to zero since nothing's changed. Nothing is moving at this point. What we actually need then is this angle right here. Okay, because I need to figure that out for force 2. Good news, force 1 and force 3 are going to be pretty easy, right? I was like, that guy, what's the angle there? 90. Mm.
120.
Say again?
120.
Oh, no.
180.
180, AKA, or I could just do it with direction 0. Yes, 180 is the full angle, just like this one. Technically, the angle here is 270, but I actually don't care about that. I care about what direction is this in. What direction is this in? Down. Yes, the down direction, all right, with the XY axis, what direction is that?
Negative.
Negative. Negative Y, or negative with our new letters IJK. Negative J. Yeah, so this is negative J, this guy's negative I, right? I can use that same formula and I'll write that out. But most of the time, I mean, if you just look, right, just look at it and be like, oh, that's in the down direction, that's in the back direction. So that's negative I, that's negative J, there's positive, I mean, so you could just like shortcut that formula by just knowing what direction you're in, because we have to do that anyway. And yes, I can also do the formula with 180 degrees, with 270 degrees, all right? Okay, sorry, back to what I was actually doing here. For force 2, because this is the only one we need to figure out. What is this angle here? I know that's 60, so what's that make this one?
60 also.
It's 60 also, right? This is what we were talking about with those alternate interior angle stuff. So, all right, that actually presents me with the angle that I need. Okay, so let's write those out one at a time. All right, so F1, all right, F1, I called that guy. So I could write this magnitude F1 cosine of 180 degrees I negative. Oh, no, I don't need the negative if I do cos that. Plus sine of 180 degrees J. Okay, what are we actually told? The weight, there's a weight 2,200 newtons. Okay, so this, all right, so this guy is 2,200 newtons. Okay, we're not told anything else. So I can do it like that, or I can just be like, okay, because cosine of 180 degrees is -1, sine of 180 degrees is 0. So I also just know this is negative. Okay, and in order to avoid writing magnitude a million times, so when you drop the vector, so magnitude of the force vector is just the scalar of that. So negative force 1 I direction. For force 2, which we called that one.
That one, I actually do want cosine of 60 degrees, I, sine of 60 degrees, J. And that is our positive given our orientation for both sine and cosine. And some numbers. This one I just wanted to make note. Okay, so once again, this, right, drops to a scalar because it's magnitude of the force, but I don't know what that force is. And since we're turning these into vectors, I know I'm going to do component by component. I do want to multiply that F2 in. So we end up with 0.5 F2I plus 0.87 F2J. All right, is everyone okay? All right, last one, F3. So again, if I was to write it out the full way, cosine of 270 degrees, right, sine of 270 degrees, right, and you could put those in your calculator, and that is a way to verify. We are back to numbers, so you can always use the numbers to do this, all right? But again, the logic helps me skip past this. Force 3 is the only one we actually had a value for, 2200. And I know that, right, the cosine goes away, there's nothing in the cosine direction, and sine 270 degrees is actually just becomes -1. Which results in, oh good, we finally have one with a number -2200 in the J direction. The big part here is since the object is sitting at equilibrium, F1 plus F2 plus F3 equals 0. All right, the object is not moving, all right, it is stationary, which means all those resultant vectors can be added together. And just plugging in what we have, right? There's our force 1, there's our force 2, there's our force 3, all right, which actually is a number. But when we add vectors, how do we add them?
X's together and the Y's together.
We add the X's together, right? We add the I's together, we add the J's together. Since we're actually looking, that means I want to add all the I's together, I want to add all the J's together.
And this sets up an equation. All right, just like we had before, the resultant force, the I's on this side, we had a resultant force of I's and J's that created something. So this is still an equation, which means that I have negative F1 plus 0.5 F2, right? Those are just the I's on the left side. What's the I on the right side? You don't know what it is?
0.
0. What's the J on the right side?
0.
Yeah. So it actually creates really nice, easy to work with equations, all right? So I can actually solve for F1 and F2. Because down here, right? I mean, this just becomes, so this one just becomes F2 equals 2200 divided by 0.87. When I get that number, I can then substitute it in here and solve for F1. This is also what we looked at before with RREF, right, with our matrix operations. So I could do this as a matrix as well. But this is super easy to do via substitution. So that actually gives me F1 equals and F2 so that actually identifies how much force each of those objects are displacing. All right, F1 is displacing 1,270 pounds. F2 is displacing 1270-ish newtons. And this one was 2540-ish newtons. So, I mean, looking at this object, okay, this one is displacing almost 2,600 pounds. This one's almost 1,300 pounds. Notice, the object only weighs 2,200 pounds. Does that make sense? This one, this is like 2,500 plus pounds, newtons. Does that make sense logically? No? I was like, with a rope and pulley, okay? I can lift an object that's well over twice my weight. Why? The angle of, it's a reduction in force with that angle, okay? If I try and pick up something straight up that is 300 pounds, I can't do it, okay? But if I offset it, I can pull something that's 300 pounds because I have an angle of motion, right? And that's what's happening here. So even though it seems like it's weird, and especially something 90 degrees, notice how little that is offsetting, okay? Because it's a bad angle, that's the whole concept, all right? The better the angle, right? And it happens to be 60, 30, 45. There are always those angles, all right? Because they offset, all right, force in good amounts, all right? Okay, to find the force, right, in vector notation. Okay, which is easy. So F1 actually back to F1 was negative I. So negative 1268.74 in the I direction. F2 2537.49 cosine of 60 degrees I plus sine 60 degrees J. And so that just specifically what the problem was asked for. The problem is basically solved once you identify the forces, right? But always want to make sure we're answering correctly. magnitude and direction. In that case, we already knew the rest of this, right? I mean, we had to know it to set up our equations. I was like, the only thing we didn't know was the actual magnitude of those forces. All right. Good stuff. Okay. Center and radius of the sphere. So this one I want to practice because, all right, completing the square, want to knock off the rust on that one. And this is a slightly more complicated version of the one we looked at last time. So find the radius, center and radius of a sphere. In order to do that, always group all your terms together to kind of see what you're looking at. So group your x's together, group your y's together. Group your z's together. Okay, so I noticed on all of them, and I mean, you noticed it up here. The term in front of the squared term on all of them is not 1. In order to complete the square, right? The term in front of x squared, y squared, z squared, whatever squared, all right, it needs to be 1. That is that a has to be 1. Now, the good news for us, all right, so we don't have to go excessively overboard on this. They're all 4. If they're all 4, all right, that means, how do I get rid of that? Divide the whole equation by 4. If they were not all 4, I would need to factor these individually. I'd have to factor out 4 of just the x's, like this was, let's pretend this one was a 5. I have to factor a 5 out of that one, all right? So I'd have to do it individually. This case, I can divide the entire equation by 4. So I'm able to divide the whole thing by 4. And again, 0 divided by 4 is still just 0. So that's even better news. Then I need to complete the square on each of these individually because they're all different. Now, the good news is that this process goes pretty fast, even though we're completing a lot of squares, all right? There's not actually much to it. All right, so let's start with the x's. What's the b term? B over 2. And then the c term?
-3/2 squared.
Yeah, I mean, yes. 9/4. I was like,
Sorry.
yes, you're absolutely correct. It is -3/2 quantity squared. And if you need that extra step, absolutely put that in. I was like, I like to just kind of like run through these because we have so many. I was like, yeah, you're right. You should put, be aware, this is b over 2 quantity squared. I was like, and that is the process you run through, all right, every time. All right, so for y, b over 2.
3/8.
3/8. And same thing, if you need to go a little slower there, put it 3/4/2/1, and then leave it, change it, flip it, right? But I mean, we can run through that pretty fast. And then what is the C term? What is it? Squared, which is 9/64. And yeah, you need to put that there just so you know, you keep pounding it in. I was like, and it's not that long of a step. All right, for the Z term.
5/4.
And important there, all right, once again, all right, we did actually see that already. So negative, right, positive, negative, make sure you have that sign there. -5/4, B/2. -5/8. And then the C, which is
25/16.
25/16. So in each of those cases, so basically I'm gonna add 9/4 here, and I'm gonna add 9/4 over here. And then right here, add 9/64, add 9/64. Plus 25/16 plus 25/16. And so what you do to one side, you do to the other. I add 9/4 over here, I add 9/4 over here, 9/64, 9/64, 25. And again, it's kind of trying to streamline that process, because with a sphere, right, we got three things going on, but it's the exact same thing every single time. Are you with me? What's the matter?
I was just curious why we, on the last one, why we squared the -5/4 instead of the -5/4.
Oh, geez, you're right. Wrote that down wrong. That's 64. Good eye. Oops. Absolutely correct. Yeah, that would hurt us. Okay, so 9/4 plus 9/64 plus 25/64, all right, yields us 89/32. Then each of these pieces. All right, I'll do the hard part on them. The first one is what? -3/2. What's the second one? And the third one? In all those cases, right? It is always the B/2 term, all right? Whatever your B/2 is, I don't need to know what it is exactly, right? It is simply just the B/2 term. All right, so from there, then I can identify, all right, what is my radius? Which piece of this is the radius? What was that? Yep. It's involved with that. So it has to do with this 89/32. All right, since everything's squared, this is also the radius squared, which means the radius is square root 89/32, whatever number that is. Okay, so that is the radius squared. And then the center, right? We have identified by putting this into sphere form, circle form, whatever, all right, you want to call it. And it is always, right, just like any other polynomial we deal with, all right? If that says minus 3/2, it is the opposite sign of that. So our x coordinate is 3/2. Our y coordinate?
-3/8.
-3/8. And our z coordinate?
5/8.
5/8. So as long as you complete square, and we all make mistakes, I was like, keep track. I was like, and then I was like, we can end up complete the square several times and then boom. All right. Is that completing a square is definitely familiar though, right? Just knocking the rust off here. Oh, and that is everything. I was like, so much good stuff. All right, so that completes our